Gentlemen, good about we are on from tonight channel, so we are going to continue with the rate laws today. And of course, if you didn't watch my video on chemical kinetics, please you should actually watch it so that at least it will give you an idea of what chemical kinetics is. So we are going to start with route law. We are going to start with the rate law. So rate law is a law that usually or that states or that trying to show the relationship between the rate of the reaction and reactant concentration. It's a law that tries to show the relationship between the rate of the reaction and the reactant concentration. Assuming now we have reaction, which means let's say we have A react to A plus B react to B, it will use CC plus D. And of course, this is the reactant particles, and these are the coefficient of the reactant particles. So small letter A and small letter B are the coefficient of the reactant particles. Small letter A and small letter B are the coefficient of reactant particles. So route law said that, so it shows the relationship between rates of the reaction. So the rate of the reaction is directly proportional to the concentration of the reactants. So rate law is directly, so according to the red law said that the rate of the reaction is directly proportional to the concentration of the reactant particles. So these are the reactant and these are the products. So the route law is just only trying to show the relationship between the concentration of these reactants and the rates of the reaction. So therefore, of course, we know that whenever we have proportionality, we introduce constant. So whenever we have proportionality, we are going to introduce constant. So therefore now, the rate is going to be T. So we introduce constant. And then concentration of the reactants. And of course, remember that whenever you have this brackets, it means, it shows reactants. So it shows concentration. It means it is concentration. So this is the concentration of the reactant. So now, let's now express this equation using route law. So how are we going to express it? So we're now going to have rates is equal to, so rates is equal to K, rate is equal to, so we now have rates is equal to K, concentration of A, and then concentration of B, and we have exponent M and N. So we should understand that this exponent here, M and N, it doesn't mean the coefficient of action. And of course, that is why here, if you can see clearly, we have small letter A here and we have small letter B. But when expressing our rate constant, we use small letter M and small letter L. Because this exponent, it doesn't mean that it is the coefficient of the reactant particles. This M and N, the M and N shows or indicate the order of the reaction. M and N means order of the reaction. It means order of the reaction. So for example, now if we have M is equal to 1, it means that we have first order reaction. And if we have M is equal to 2, it means that it is second order. The reaction is second order. The reaction second order is second order to A. The reaction is second order to A. And of course, if we have N is equal to 1, it means that the reaction is also first order. So now, for example, we can have N here, the N here, it can also be 1. So if we have N is equal to 1, it means that we also have first order reactions. It means that we have first order reaction. So it means that we have n is equal to 1, it means that we have first order. The reaction is first order to B. The reaction is first order to B. So, and we have what we call overall order of the reaction. How do we get overall order of the reaction? To get the overall order of the reaction is just to sum the exponents. The exponents, like for example, here our exponent is m and n. So to know the order of the reaction, you are just going to say m. We are going to have m plus n. So m plus n will give us overall order of the reaction. To give us overall order of the reaction. So if you now sum the exponents, and of course, as I said, this m and n, or which is called order of the reactions, it can only be determined experimentally. You cannot know it by just merely looking at it. Rather, you can only know them using experimental method or from the initial concentration of the reactant particle. So from there, you can simply get that. Okay. So now, for example, assuming now we have a reaction between nitrogen oxide and carbon monoxide and nitrous oxide from carbon dioxide. So now if we want to express the rates of this reaction, we can have some conjunctions. Rates is equal to K NO2. NO2, then we have 2 rates. Do you know that we can actually have the expression of this to be like this? And what does that mean? It means that generally when we are thinking about rate flow, it's just trying to show the relationship between the rates of the reaction and the concentration of the reacting particles. So, but you can actually get something like this from here. It means that we know CO. Is it that we really ignore it? No. It's because if it doesn't have this from here, if I didn't express this from here, it tells us that this CO is zero order. It means that the rate of the reaction doesn't depend on the concentration of CO here. But of course, you can have it like this. So, but if you have it like this, it means that when you are expressing the route flow, it gives us an idea that the rate of the reaction depends on both the concentration of NO2 and CO here. And of course, we can get the overall order of this reaction. So how are we going to say, how are we going to get the overall order of this reaction? Is by saying overall order of the reaction. So the overall order of the reaction is just 3. So it's just 2. We have 2 here and here we have 1. So 2 plus 1, we have 3. So it means that the reaction is third order. The reaction is third order. But if it doesn't have this, if here we don't have this, it means that the overall order of the reaction is second order. And it means that also the reaction doesn't, or the rate of the reaction, it doesn't depend on the concentration of carbon monoxide. So that is what you call order of the reaction and rate flow. So that is what the rate law is trying to tell us. It's just trying to give us the relationship between the rate of the reaction and the concentration of the reacting particles. And of course, in the route flow, we have a constant which is K, and the constant is called rate constant. It's called rate constant. And at the same time, we have what they call order of the reaction. We can have first order reaction, we can have second order reaction. Like for example, in this case, the order of the reaction, this reaction is second order to NO2. And since there is no CO here, it means that it is zero order to carbon dioxide. And the overall order of the reaction is 2, because this is 0. So that is why it is not even expressed here. So this is what we call second order reaction. Overall order reaction is second order and it's also second order to MO2. Okay. So now we are going to look at the unit of rate constant. And how are we going to get the unit of rate constant? I think from here we can just simply understand it's simple that rates is equal to K times concentration of reactants. Concentration of reactant. And of course, to get the unit of the rate constant, you can simply make K subject of the formula. We can simply make K subject of the formula. Therefore, we have K is equal to, we are going to have rates. We are going to have rates all over reactant concentration, all over reactants concentration. And of course, from my previous video, we know that the SI unit of rate is molar per second. And of course, the unit of concentration of the reactant, the concentration of reactant is always expressed as molar. But we should understand something here very important. So if we just leave it the way it is before, that will be a problem because we don't know the order of the reaction. So that is where we use Y to represent the order of the reaction. And of course, here we are going to also have Y as the order of the reaction. So now, what we are going to do here is that it means that our rate constant is equal to molar per second divided by molar raised to the power of the rates. So the raised to the power of the order of action. And this will represent order of action. So that is why to know the unit of this rate constant is also depend on the order of the reaction. Like for example now, if this reaction is first order, if this reaction is first order, what does that mean? It means that if this reaction is first order, so what is going to be the units of the rate constant? So if it is first order, it means that clearly we can see that here the power of this is 1. So if the power of this is 1, then what is going to be the SI unit? It means that we're going to be per second because this term will now cancel this term. So it's going to be per second. It's going to be per second. Okay? So that is, so if it is first order, it means that K, if it is first order, it means that K is going to be per second. But what if it is a zero order? So if it is zero order, of course from here we have molar per second divided by molar. So here we have 1. So if it is zero order, it means that our Y is equal to 0. So if Y is equal to 0, it means that here we are going to have 0 here. So any number raised to the power of 0 is 1. So therefore this will now take care. Because here we are going to have 1. So at the end, for the 0 order, so this is for the first order. And of course for the 0 order, this is what we are going to have. This is what we are going to have. Because this one is 1, so we are going to have our K is going to be molar per second. It's going to be molar per second. So what if it is a second order reaction? If it is a second order reaction, it means that here we have our M. We have our M here. So therefore it is going to be in a form of square. It's going to be in a form of square. So we have it in a form of square. So therefore at the end, what will happen, this one will now take care of this. So we are now going to have left with only 1 M. So therefore at the end, the SI units, or at the end, the SI unit of K for the second order is going to be the K for the second order reaction is going, because we have m here. So then we are going to have per mole per second. So we per molar per second. We are going to have per molar per second because this one is 1 over s, and of course we have m here over 1, yes. This one will now cancel this. Yeah, of course. So we are now going to have per molar per second, and that is for the third order reaction. So it means that the units or the unit of rate constant, depend on the order. If it is first order reaction is per second. If it is a zero order reaction, is going to be molar per second. And if it is going to be if it is the second, for the zero order is molar per second, and for the second order is going to be for molar per second. Okay.